Okay, so this is an example one-dimensional kinematics problem. This is a problem that I used on a homework quiz a few years ago, and at the request of Jacob Zucker, because his girlfriend, Katie Morley, was in my sixth period class, and this is how he asked her to homecoming. Of course, it ended up being a much harder problem than I intended, so a lot of people ended up being angry at Jacob when it wasn't really his fault. But anyhow, I think it makes a good example problem. So what we have is the situation where, let me see now if I can start doing this correctly. So here's the train platform, and here's Zucker. Okay, and he starts there. The train starts here, and Zucker is running towards the train at a constant speed. I'm going to call that V sub z equals 9.00 meters per second. Okay, and the train is accelerating. Initially, it's a rest, but it's accelerating this way at a rate of a. I'm going to call it a sub t. So t for train is 1.25 meters per second squared. Sorry about that little thing that just flashed up there. The initial distance between them, I'm going to call, I like to give names for everything. I'm going to call D, which is 15.0 meters. The train has an initial velocity, I'm going to call it VT0 of 0. It's initially at rest. Okay, so at some point, Zucker catches up the train, we hope, and we've got to find out when that happens. So first I want to set up an axis, or set up a coordinate axis for this. I'm going to choose to have x, positive x, be going to the right, which is the direction the train and Jacob are both moving. And then the question is, do I want to, where do I want to set my origin? It doesn't matter. You can set the origin anywhere. It's convenient. It's most convenient to set it probably at one of the two locations of the train or of Zucker, the initial locations, because then you get to use 0 for one of your initial positions. So I'm going to say x equals 0 here. So what I'm going to do is I'm going to say the initial state, which I'm going to call 0. Okay, it's a 0 with a circle around it. We have Zucker is initially at, and this is x of Zucker at state 0, okay, is initially 15 meters behind the train, which means he's initially at negative d, okay, and Zucker's velocity we know is constant, vz is constant, and let's see, the train initially, so xt0, the train's initially at the 0, at the origin, and the train's initial velocity is 0. And of course, the train is accelerating at a constant rate. Okay, so what we want to do now is we want to find out at what time Zucker will be able to catch up with the last car of the train. And the last car of the train is what we're, talking about the position of here with these variables. Okay, so this is the point that Zucker needs to catch up with. So the way to do this is to think, well, what at the final state, okay, at the final state, what is the condition that has to be satisfied? And if you think about that, the condition that has to be satisfied is that Zucker has to be at the same point as the last car of the train, which means their x-coordinates have to be the same. When two things have to be in the same place, then they have to have the same coordinates. That's kind of obvious when you think about it, but it's one of these things that's very obvious once you know it, but hard until then. So what we do now is we apply the cake equations to both the train and to Zucker, and then we solve for when the two x's are the same. So let me do it for Zucker first. Okay, so here I'm doing the cake equation for Zucker. Actually, the cake equation I'm going to use, I'll just write down here, is delta x equals the initial velocity times delta t, And what I'm going to do is I'm going to set time equal to 0 at the beginning. So initially, I'm going to say my initial conditions here have time 0, and the final condition will be time t. So I guess you would say t equals t, okay? And so I'm going to just write in t instead of delta t. It makes things a little easier. And plus 1/2 at, excuse me, that's an a, there we go, at squared. So this is your cake equation. And you can expand the delta x to be x minus x naught, okay, which then equals all this stuff, v naught t plus 1/2 at squared. Okay, so what I'm going to do for Zucker now is I'm going to apply this, and I'm going to say Zucker's x position minus 0. So I'm taking this here and applying this to Zucker. Zucker's x position minus Zucker's initial x position, which is, whoops, I already did it wrong. So let me back up. Okay, minus his initial x position, which is negative d, okay, because we have that up here, okay, equals Zucker's initial velocity, which is just his constant velocity, times t. And then Zucker is not accelerating. Zucker has no acceleration because he's going at a constant velocity, right? So therefore, this last term is going to go away for Zucker. So what you get here, this is just applying this term, this equation to Zucker. You get x for Zucker equals bzt, and then he is at, what have I done wrong here? Vzt, I feel like I'm doing something wrong. No, I guess not. No, right, because this would be a plus d, and then I'm going to subtract over. Okay, so I've got this right. Okay, so this is position of Zucker, okay? And then I want to do the train. So, and by the way, I apologize for being so incredibly disorganized in my work, but that's me. Okay, so for the train, what we're going to have now is that, let's see, I don't want to do this. I'll do it down here. X for the train minus the train's initial x position, which is 0. So I'm just going to say xt minus 0 equals, and then the train's initial velocity is 0. So we can ignore this first term for the train. Okay, and then we just go with 1/2 times the train's acceleration times t squared. So x for the train equals 1/2 acceleration of the train times t squared. Okay, actually I don't want to, let's see. I'm not going to box that because it's not an answer. I'm going to start with this little squiggly thing around it, like this. So now these are the two things we plug into here, okay, because our final condition is these two have to be equal. So what you're going to get is that, let's see, Zucker's final position, which is Vz times t minus d, has to equal the train's final position, which is 1/2 a sub t times t squared. And then we rearrange things a bit, and we can make it a quadratic equation. If you don't remember the quadratic formula, you better pull out the old Algebra 2 book, or the old Algebra 2 notes, or whatever, and learn it. So 1/2 a sub t times t squared, and then we're going to have a minus v sub z, okay, times t, let's see, plus d is all going to equal 0. And this is a quadratic equation t, which was what we were asked to solve for. We're asked for how long, right? How long? And actually, maybe we should have said that's that. Maybe we should have said that was an unknown. But there we go. And so what you get, whoops, oh my god. Okay, we're still recording, so let's see if I can undo that. And yay, okay, I'm fortunate here. So what you get, and so when you go through the quadratic formula, I'm not going to do it here, but when you go through the quadratic formula, what you'll get is t equals, let's see, you're going to get t equals, so it's negative v, actually I'm going to go for the quadratic formula. So t equals vz over at plus or minus square root of vz squared and it's minus 4ac, so but that's all over 2a as well. So let's see. I'm just gonna back up here. I don't really have space to finish this out, but what you get when you do the math and plug these in, you get, when you plug in these values for Zucker's velocity is 9.0 meters per second, positive. The train's acceleration is 1.25 meters per second squared, and when Zucker's initial position is 15 meters back, what you get is that Zucker takes 5.24 seconds, or, and this is because, remember, the quadratic formula is going to give you a, the plus or minus. So 5.24 seconds or 9.16 seconds. And so these are the two answers. Now, which one is right? What's going on here? Why do we have two answers? So I'm going to show you here that what happens is, let me see if I can actually do what I did accidentally intentionally. Yes. Okay. So what happens is, I'm going to show you now, here's a position versus time plot. Horribly done, but it should give you the idea. Let me see if I can change colors. So I believe I can. So I'm going to try for green. So I'm going to try doing the train in this neon green color. Let's say the train starts out here, right? We said the train started out at 0. We made that the origin at time 0. So the train starts out here. Initially it's motionless, but then it begins accelerating at a constant rate, which means its position versus time plot looks like a parabola. So you get something like that. Now, here's the very tricky one. We'll try blue for Zucker. And Zucker starts out some distance back, right? And then he starts running at a constant speed. What happens is he catches up to the train right about there, and all is fine and dandy. But if he were to keep going, he would catch up to the train again. So what happens here, if you think about it, time is going to the right, remember? So what happens is, as time goes by, Zucker catches up the train, and then he reaches the last car of the train. He passes it, and he gets some distance ahead, right? But the train is still constantly accelerating, so it's speeding up behind him, and then the train starts moving faster than him, so then the train passes him, and he has another shot at jumping on. So that's why you get the two answers. So this is equivalent to like the 5.2 answer I think we got, and this is equivalent to the 9.2 or whatever it was. So I hope that makes it clear what's going on here. Now, when you do a problem that uses where you have to use the quadratic formula, or even where you have to take a square root, you'll get two different answers. So you have to think about them. This is not, in math, you just have a math problem with numbers, and you're allowed to give two different answers. But here, we need to know how long it takes Zucker to catch the train. And I think the correct answer, if you interpret the problem, the reasonable way, is this amount of time, because this is his first chance to get on the train. So you want to know how long does it take him to catch up the train. If he's smart, he hops on here, and he doesn't have to keep running this far. So anyway, that's that problem. I hope this helps you with the web assignment you've got. These examples show basically how I like to approach these problems, and I think this should make the web assign doable. So good luck.